Now we're going to utilize the symmetries of the unit circle in order to discover some facts about the sine and the cosine. For example, what can we say about these 2 points here that corresponds to this ray and this ray? Well, they have the same sign, because the sine is the vertical projection onto the y-axis. And as you can see, it is the same for both points, for this point and this length, and it's in both cases with a positive sign. So what's the conclusion of all that? Well, if this angle here is alpha, and then this angle here should also be alpha because of symmetry. And now, this ray must correspond to an angle of alpha. And this one must correspond to an angle of, let's track, 180 minus alpha. And so the sine of alpha equals the sine of 180 minus alpha. Now let's consider another symmetry. For example, if we continue this line and we take this ray, and let's see where its sine goes. Well, we know that this angle here is alpha because of symmetry, and now the length of this segment must equal the length of this segment, again because of symmetry. For example, symmetry across this x-axis. But now this is on the negative side of the y-axis, and so this length has negative sine and this length has positive sine. And therefore, sine of 180 plus alpha equals the negative of sine of alpha, which is the length of this segment. And finally, let's continue this line like this. So what's going to be this angle? It's going to be alpha, again because of symmetry. And now the sine of this point is going to be this length with a negative sign. So we know that sine of alpha equals this segment, positive, and then sine of 360 minus alpha equals this length, negative. And therefore, sine of alpha equals minus sine of 360 minus alpha. Also, this ray not only corresponds to 360 minus alpha, it also corresponds to just the angle minus alpha, because we start from here and we rotate in the opposite direction alpha. So it's as if we got 0 minus alpha. So this corresponds to the angle minus alpha. So this here corresponds to the sine of minus alpha. And so we got that sine of minus alpha equals minus sine of alpha. Now let's consider the cosine. So we must first draw the projections to the horizontal axis. And now we can see that the length of this segment equals the length of this segment. But this length we count with a negative sign, and this length we count with a positive sign. And so the cosine of 180 minus alpha equals minus cosine of alpha. Also, cosine of 180 plus alpha equals minus cosine of alpha. And lastly, cosine of 360 minus alpha equals cosine of alpha, or cosine of minus alpha equals cosine of alpha. Because the cosine of alpha is the length of this segment, cosine of minus alpha is the length of this segment, cosine of 180 minus alpha is the length of this segment here, but with a negative sign, cosine of 180 plus alpha is the length of this segment, but with a negative sign. So of course you don't need to remember all these formulas. You just need to be able to imagine the unit circle and how the symmetries in the unit circle work. And so every time you need, for example, the sine of 180 minus alpha, you can imagine, oh, this corresponds to this point on the unit circle, and the sine corresponds to this segment, which is the same as the sine of the angle alpha, which also corresponds to this segment. Another important observation is that we can scale the whole unit circle by a factor of k, keeping that center constant. Or in other words, we can apply homotopy to the unit circle with this center. In this case, the radius of the circle will become r instead of 1. Now let's see how this translates to our knowledge of sines and cosines. So let this be the circle of radius 1, so let this be the unit circle, and let this be the scaled circle such that its radius is r. Then I'm going to take an angle alpha, and I'm going to see how the sine and the cosine of alpha relate with the segments here on the scaled circle. Now you can agree with me that on the unit circle, this length here is the sine of alpha, and this length here is the cosine of alpha. Because this is a rectangle, and so this segment, which equals the sine of alpha, equals also this segment. Now we can consider this triangle and this triangle. They are similar triangles because they have the same angles. They share the angle alpha and they have right angles here and here. And so their sides are proportional to one another. Or alternatively, we can use the intercept theorem, which tells us that because this line is parallel to this line, then these two triangles are similar, or their sides are proportional. And we know that the coefficient of scaling is r. And we can see this, for example, on this line, because we have this is 1 and this is r. So the ratio of the corresponding sides of the similar triangles is 1 divided by r. And so all sides of this triangle are r times larger than all the corresponding sides of this small triangle. And now since this length is sine of alpha, then this length must be r times sine of alpha. And analogously, because this length here is cosine of alpha, then this length here is r times the cosine of alpha. So in conclusion, we got that if instead of taking the unit circle, we took a circle with radius r, then this segment doesn't correspond to sine of alpha, but corresponds to r times sine of alpha. And this doesn't correspond to cosine of alpha, but corresponds to r times cosine of alpha. And that's because the hypotenuse doesn't correspond to 1, as in the previous case, but it corresponds to r, because we increased the radius r times. And so we increased the lengths of all segments by a factor of r. So for example, if I take an angle beta, like this, then this length is going to be r times the sine of beta, and it's going to be positive. And this length here is going to be r times the cosine of beta, and the cosine of beta is going to be negative, so this length is going to be negative. Today there are a lot of optional problems, because they're quite easy. Prove that sine of 90 plus x equals sine of 90 minus x, cosine of 270 minus x equals negative cosine of 270 plus x, and find sine of 45 and cosine of 45. And here is the solution. First, we need to draw the unit circle. Now, sine of 90 plus x would look like this. 90 plus x more, so somewhere here, this point, such that this angle here is x. And then 90 minus x would be 90 and then minus x. So the point will be somewhere here. And now, because of symmetry, we would get that this angle here is 90 degrees. And therefore, sine of 90 degrees plus x is going to equal this segment. And sine of 90 degrees minus x, which is this, is going to equal this segment. So it's the same segment, therefore the two sines are equal. And the reasoning for the second part is absolutely the same. We have 270 minus x, which is this point here, and 270 plus x, which is this point here. So the cosine of this point will be this distance, which is on the negative side, and the cosine of this point will be this distance, which is on the positive side. And because of symmetry, for example, with respect to this y-axis, this length equals this length. And so the cosine of one equals negative the cosine of the other. And the negative comes because they lie on opposite sides of the x-axis. For the sine and the cosine of 45 degrees, we just need to notice that the sum of the angles in this triangle is 180, and therefore the other angle here is also 45 degrees. And so it's an isosceles triangle. Therefore, this length equals this length, and let's call it x. And we know that the unit circle has radius 1, so this side is 1. And now we can apply the Pythagorean theorem for this right-angled triangle. And then we get x squared plus x squared equals 1, 2x squared equals 1, x squared equals a half, or x equals square root of 2 divided by 2. And so x is square root of 2 divided by 2. And x in this case is both the sine and the cosine of 45 degrees.